Hi everyone, this is our third lecture on section 6.6, and this one is about the vector surface integral. So for the vector surface integral, we start with, consider a 3D vector field. Okay, 3D vector field, F equal to P, X, Y, Z, so three variables, Q, X, Y, Z, R, X, Y, Z. And a two-sided surface, S, and we put an arrow onto it to mean that it's oriented from side 1 to side 2. You may be curious as to what a surface that doesn't have two sides is. There are one-sided surfaces. The only such thing that actually exists in 3 dimensions is the Mobius band. So, side note, the only one-sided surface which exists, well, that's not exactly right. Not the only. So, a one-sided surface which exists in 3D is the famous Mobius band. And the Mobius band looks like this. There's this rectangular strip that's got twist to it. Suppose I didn't quite draw that right. Whoa. That's fine. So it's this rectangular strip that's got this half turn to it. And that actually only has one side. Because, I mean, normally I would show you a piece of paper twisted into a Mobius band, but in lieu of that, we have to go with this. If you walk along the surface here, so walking, and then I come to here, now I'm going to flip underneath this curve. So whereas I started up here, and I walk along here, imagine yourself standing straight up like that, and walking along here, then you will sort of flip upside down. And suddenly you're upside down. So I walked from this part of the surface to that part of the surface without actually leaving the surface. Thus, the surface only has one side. It only has one side, and the boundary of the surface is actually a circle rather than like two circles, which maybe it might look like. So that's a one-sided surface. But we're not dealing with those. We're only dealing with two-sided surfaces. So we have a 3D vector field and a two-sided surface oriented from side 1 to side 2. Right? You need two sides to actually do that, to orient it. At each point on the surface, consider the vector force vector f x y z. So you've got this surface. It's got two-sided. The surface may be closed like a sphere or something like that, in which case it has like an inside and an outside. So here's this surface here. And at any point, you consider the f of the vector field. So this is f, and then the surface itself is going in this direction. So down here, that's the underside, and this is the overside. So we're oriented in that direction. Okay, so you consider this vector. The part of the vector f that goes perpendicular to s so the component of f that is perpendicular to s is considered to be flowing across s. The component of f that's tangent is not, of course, right? Obviously. Right? We're interested in the amount of the force that's flowing through or across that field. The vector flux across S. So how does one isolate the component of F that's going across S? Oh, so we are interested in the total amount of F cross S. So often called the vector flux. Or flow across S. Okay, so how do we isolate these ingredients? How do we isolate the bit of F that's going across S, the bit of F that's perpendicular to S? Okay, the surface S is represented using parametric equations, as parametrized. As a parametric function. R of uv, right, equal to x uv, y uv, z uv. Right? Two vectors that are therefore tangent to S are the partial derivatives of r with respect to u and v. So two tangents are therefore the derivatives, partial derivatives, ru partial derivative of r with respect to u, and the partial derivative of r with respect to v. So you've got this surface here. Okay, you've got this surface, and you're looking at this point here. Here are those tangent vectors. So this is the surface S, and the surface S is going to be oriented from side 1 to side 2. Say it's this way. So now you've got these two tangents, right? Partial derivative of r with respect to u, say, and partial derivative of r with respect to v. So those guys are tangent, so the vector that's going to be perpendicular to the surface is a vector that's perpendicular to both of these, which is the cross product, right? So you want the cross product that points in the same direction, right? So this one, it's given by your right hand. You take your right hand and you curl your fingers in the direction from U to V, and then your thumb points in the general direction of RU cross RV. In this case, it's in this direction, the same direction as S. RU cross RV, which is perpendicular to this vector, perpendicular to this vector, and therefore perpendicular to S itself. So RU cross RV, so either RU cross RV is perpendicular this, or RV cross, well, both RU cross RV and RV cross RU are perpendicular to S. However, only one of them points in the same direction. Side 1 to side 2, which is the direction which is the orientation of S itself. Right? The right-hand rule distinguishes which. So in this picture over here, it's RU cross RV, right? Let me do another example in a moment. Well, let me do another example. So this is a basic example. So given surface z equal to fxy parameterized as rxy equal to x is x, y is y, and z is fx, y, like that. So given this surface parameterized like this, oriented in the upward direction, so what's that look like? So you've got this surface satisfying the vertical line rule for z equal to f of xy. So here's that surface. And it's sort of vaguely oriented in the upward direction. So oriented this way. Okay, well, if this is the x-axis and this is the y-axis, then the partial derivative of r with respect to x is in this direction, because it's with respect to x, and the partial derivative of r with respect to y is in that direction. So, like, here would be rx and ry. Let me try that again. Right, that's rx, this is ry. So the one that points in the upward direction is rx cross ry, because the right-hand rule curls your fingers in the direction from x to y. And therefore, for the thumb to be pointing upward, on your right hand, you have to be going in the direction from x to y. So perpendicular here, perpendicular here. The direction for Rx is this way, the direction for Ry is that way, so Rx cross Ry goes up, Ry cross Rx goes down. So given this, parameterizes that, and oriented in the upward z direction, the cross product Rx cross Ry points upward. Okay? So that cross product points in the upward z direction as well. All right, so to isolate the component of the force vector field, the vector field F that is perpendicular to S, you want to take a dot product. But you don't want that dot product to be affected by the size of the cross product. So then you take this, what's known as unit normal vector. So RU cross RV is perpendicular to S. And points from side 1 to side 2. Which is the direction for S. Therefore, the unit normal function n equal to RU cross RV over the length of RU cross RV points in the same direction and has length 1. And has length 1. Therefore, the component of force F that is perpendicular to and moves from side 1 to side 2 is just F dot n. So at any given point, the amount of the vector field that's flowing across S is F dot this unit normal function. So we define the flux of F across the oriented surface S as the scalar surface integral, double integral over S, so now it's not oriented anymore, of f, the scalar function. So that's a dot product, but a dot product gives you a scalar function, f dot n ds. So that's the definition of the thing. That's the total amount you're summing up. You're summing up the amount of f that flows across S. The amount of f that flows across S is f dot n. And you're just taking the sum of that over the entirety of S. So the sum of a function over the entirety of the surface S is the scalar surface integral. This is a scalar function. It's a dot product of two vector functions. A dot product of two vector functions give you a scalar function. So this scalar function measures the correct thing that we want to measure, the flow of the vector field across S. So now you just take the surface integral of that vector, of that scalar function. Now, when you want to calculate it, it doesn't quite go like this. That's the definition of it. That's of this surface integral. So one way to refer to it is this. So we refer, well, let me do this first. How do we calculate the double integral over S, f dot n ds? Well, remember, right, the surface integral of f x y z over S ds is equal to, right, the double integral over R, where S is given by R of uv for u and v in this region R. So the scalar surface integral is the double integral, right? This is the surface integral. The scalar surface integral of fxyz ds, where the surface S is given by the parametric function R of uv over some region R, is the double integral of f of R of u of v, the length of RU cross RV dA. So the surface integral is calculated as a double integral in terms of variables u and v, whatever u and v might be, x and y, r and theta, theta and phi, t and phi, t and theta. There's all kind of different ways in which the two variables are. The two variables are not necessarily x and y, although a lot of our examples it will be. All right, so now, right, the surface integral of f dot n, and this is pretty cool, is equal to, where S is given by u of v, again, R of uv, is equal to the double integral over R, f of R of u and v, dot, the n is RU cross RV over the length of RU cross RV. But when you change, so this is F, this is N. But when you change the surface integral into a double integral, you get this. dA. Oops. Well, but now it cancels. These guys cancel. So you get, it's the double integral over R of f of R of uv dot RU cross RV dA. just like the scalar formula in a lot of ways. Just like the scalar formula in a lot of ways. So if RU cross RV points with the orientation of S, rather than RV cross RU, then, so let's just sum it up. The double integral f dot n ds is equal to the double integral f of r of uv dot ru cross rv dA. So that's the vector surface integral. That's the definition of the thing. That's how it's calculated. Pretty cool. So the surface integral is referred to like this, and sometimes it's referred to as this. Instead of double integral of s f dot n ds, we write double integral. You use this f dot, and then this bit here is denoted as ds. So there's two ways to refer to the surface integral. The surface integral over the oriented surface, s arrow, f dot ds with an arrow on the s, or f dot n ds, which is the scalar surface integral. But it's always calculated like that. Not always. Sometimes you might do it like this. I'll actually do an example where you actually use this one, where you don't do this cancellation bit here. But most examples you do that. Okay, so we refer to the surface integral this way, to refer to the vector surface integral. All right, for example. Okay. So, for example, take the vector field yx z squared, like that, and calculate f dot s, f dot ds, so I'll use that one, where s is the surface z equal to 4 minus x squared minus y squared above the xy plane. Oriented upwards. Okay, so I'm using that this type of function, a surface z equal to f of x, y, oriented in the upward direction. So in this case, the cross product that we're going to want is rx cross ry. So a picture of what we got going on here. So we have the parabola pointing downward, and right, so this is the surface z equal to 4 minus x squared minus y squared. This right here, so this is 4 right here, So this right here, this happens when z is equal to 0, this intersection with the xy plane. So 0 equals 4 minus x squared minus y squared. You got x squared plus y squared equal to 2. So this is the circle of radius 2 in the xy plane. And this surface is oriented in the upward direction. Calculate the flux of F across S. Okay, so I'm going to parameterize in the standard way. So use parameterization for a function z equal to fxy. Use this standard, sometimes called the trivial parameterization. X is x, y is y, and z equals f of xy. Right? For the circle of radius 2. In the xy plane. Okay, well, first let's take partial derivatives. Partial derivative is 1. Partial derivative with respect to x, 1, 0, minus 2x. Partial derivative with respect to y is 0, 1, minus 2y. Which cross product do we want? Right? Rx is in this direction, Ry is in that direction. So Rx cross Ry is the cross product that we want, because that's the one that points up. Is therefore equal to I, J, K, 1, 0, minus 2x, 0, 1, minus 2y. So this is equal to 2x, right? And then 2y, and then 1. All right, so that's Rx cross Ry. That's the cross product that we want, rather than Ry cross Rx, which points down. The only difference between the two, however, as far as affecting the answer goes, is it just negates the answer. Because it's the same vector, just negated. Right? It would be minus 2x, minus 2y, 1. And all that's going to do is negate the cross product, that product. Oh, by the way, the vector field x is what? Is yx z squared. So f of r of xy is equal to, well, x is equal to x, right? Rxy. X is x, y is y, and z is this. So even this step is sort of simplified. So y is y, x is x, and z is 4 minus x squared minus y squared, a whole schmear there, quantity squared. So that's z squared. So the flux is double integral over s f dot ds is equal to the double integral over r, right, where r was that circle of radius 2 for x and y. Right, that's the shadow of that paraboloid when you project it straight down into the xy plane. Right, is that circle of radius 2. So all the points of the paraboloid occur above that circle of radius 2, or the inside of it, the disk of radius 2. So this is f of r of x, y, dot rx cross ry dA, right? So this is equal to double integral over r. That's the f, yx 4 minus x squared minus y squared dot rx cross ry is 2x, 2y, 1 dA. Notice we haven't put the bounds on the integral yet. We're still setting the thing up, the double integral. So it's double integral over r, 2xy plus 2xy plus 4 minus x squared minus y squared squared. Okay, still got some simplifying to do. Double integral over r, 4xy plus 4 minus x squared. I'm going to write it like that. So how would I calculate this? So now that I've expressed the double integral in the final simplified form here, now the question is, how do I calculate the double integral? So the surface area, the flux integral, not the surface area, the surface integral, the total flux integral, reduces to a double integral. Once you get it in terms of the double integral, now we ask ourselves, how do we want to calculate that double integral? This one, obviously, you want to use polar coordinates because r is the disk, right? So r is 0 less than or equal to radius r less than or equal to 2, 0 less than or equal to theta less than or equal to 2 pi, because this is a whole disk. So it's double integral from 0 to 2, 0 to 2 pi, 4r squared cosine theta sine theta plus 4 minus x squared plus y squared is just r squared times r dr d theta. Okay? So multiplying through, remember that correction factor. Multiplying that through, so this is 4r to the third cosine theta sine of theta. And make sure you put a parentheses around that whole expression when you have a sum, because that r needs to be distributed through the whole sum. A lot of times it hasn't been a sum, but this time it is. Plus r times 4 minus r squared dr d theta. Okay, antiderivative with regard to r. So that's just r to the fourth. Right, and these are constants, cosine theta, sine theta. Plus this one, 1/6 minus 1/6, 4 minus r squared to the third. So here you would let u equal 4 minus r squared. And then you're going to get, in the end there, minus 1/6, 4 minus r squared to the third power. Right? We can double check that. So 3 times 1/6 gives you 1/2. 4 minus r squared times the derivative of the inside, 2r, so the minus 2 and the minus 1/2 cancel, or to the third power, to the second power, leaving you with r, 4 minus r squared squared. Right? So that is the antiderivative. Evaluated from 0 to 2, and we still got to do the d theta. So this is equal to the integral from 0 to 2 pi, 16 cosine theta sine of theta minus 1/6, and then at 2 this is 0, and then at 0 it's 4 to the third d theta. So integral from 0 to 2 pi. Now 2 sine theta cosine theta, I'm going to use this formula for it, is sine 2 theta. Sine 2 theta is 2 sine theta cosine theta, so this is 8 sine 2 theta. And then this becomes plus 6, so 4 to the third is 64 over 6 d theta. So antiderivative of this, well, the antiderivative of that is going to be cosine. It's going to be 0, right? Because sine 2 theta, sine 2 theta from 0 to pi does one wiggle. So we're going to 2 pi. So sine theta is going to wiggle twice. Right, so that's y equals sine 2x. So that's just 0. So we're going to have 2 pi times this. That's 64. So 64 times 2, 128 pi over 6. Divide that by 2, 64 pi over 3. Okay, so that's that vector flux surface integral, one example. Let's try one more. So consider the following. F equal to, so this is 1 over x squared plus y squared plus z squared. So this is a scalar function, x squared plus y squared plus z squared to the 3 halves times x, y, z. Right, so this scalar gets multiplied through there. So this is actually equal to this vector v over the length of v to the third. And so that's v over the length of v to the third. So it points straight from the origin at each point x, y, z. So this is x, y, z right here. So this vector is v. So v over v to the third is going to be like right here. Right. At each point x, y, z, you've got this vector whose length decreases proportional to the inverse of its own length. So actually it's going to be even smaller than that probably. Pretty dinky. Okay, so now let S be the sphere of radius k oriented from the inside to the outside. The sphere of radius k oriented from the inside to the outside. Okay, so what is the, so now I'm going to go to f dot n. So remember, there was two ways to refer to this surface integral. So calculate the flux of f across S. Calculate the flux of the vector field across the surface of the sphere. Now remember, this by its very definition, so the original definition, is the scalar surface integral, right, of the vector field f dot the unit normal vector n. ds. Okay, so without ever actually finding a parameterization, without ever actually having to find the parameterization, let's just write out what these vectors are. So this is the vector v over the length of v to the third. That's what f was. What is the unit normal to the surface? What is perpendicular to the sphere? Right? Perpendicular to the sphere is its radius. The radius of a sphere is always perpendicular to it. So at any point v on the sphere, what is perpendicular and normal to it is v itself. So what is perpendicular to the sphere at the point v is v itself. But then you want it to have length 1. So it's v over the length of v, ds. Right? Scalar surface integral, which is equal to the scalar surface integral. V dot v is the length of v squared. Well, let's write it this way. Let's do an extra step. V dot v over the length of v to the fourth. But v dot v is the length of v squared. Right, so this is 1 over the length of v squared. But S is the sphere of radius k, so that's a constant, 1 over k squared. So the length of v is k. So, well, this is a constant, so I can factor it out. 1 ds, which is equal to 1 over k squared times the surface area of the sphere. Which is 4 pi k squared. That's a known formula. I think we didn't actually ever calculate that. Maybe we'll do that as an example. But anyway, the k's cancel and you get 4 pi. Whoa, a constant independent of k. This is a constant which is independent of k. Therefore, right, the force F equal to the vector v over the length of v to the third. Therefore, the force F of an explosion vector field. Therefore, the force field F produced by an explosion at the origin is accurately modeled, is the way to say it. Because when you have an explosive force, right, so you have some explosion at the origin, and then it produces an explosive force just straight outward from the origin. So the vector F is always going to be parallel to the line straight from the center to that point. But the further away you go from the origin, the less the force is at any one given point, right? So the force gets weaker and weaker at any one given point. So if you've got a really, really large sphere, right, the force of the explosion felt at one point on the sphere is small. But the total flux of the vector field across the sphere, has to be the same, no matter how big the sphere is, because the energy is just simply flowing from the origin and going out, as long as it's not sort of dissipating in some other way, because of wind or heat or whatever the case might be. Okay, so that's a vector field that accurately models that physical phenomenon. Okay, so that is the end of the lecture on this section.